This PhysCast is looking at an electric dipole sitting in an external electric field. Pause the video and read through the question carefully. Now that you've read through the question, let's begin with our interpret step, thinking about what the question is really about. It should be clear here we have an electric dipole. Got to think about what an electric dipole is, and it's in an external electric field. It's important, it's not just the electric field from the dipole, it's an applied electric field that the dipole is sitting in, and the question is asking us about things like the force on the dipole, the torque on the dipole, and the electric potential energy of this system. As we would often like to do in our develop step, drawing a diagram here will help us quite a lot. So let's think about having our electric field. So here we might have our field indicated by the lines, and we've got a dipole sitting in this uniform electric field. So our dipole, remember, consists of two charges, a positive charge and an equal magnitude negative charge, separated by some distance that we might call small d here, the distance between those two charges. And we can kind of define this thing by a single quantity we call the dipole moment. We make that a vector here, something here we call P, and that P vector there, the dipole moment, we can simply write the magnitude of that will be equal to the magnitude of each of the charges multiplied by that separation between them. And we also might be interested in the angle between that dipole moment and the electric field. Because if we go back and remember, we can think about the torque acting upon this dipole equal to the cross product of these two vectors, the dipole moment and the electric field. And in terms of the magnitude of that torque, it will be the magnitude of the dipole moment multiplied by the magnitude of the electric field times the sine of the angle between them. That angle in there is quite important. We can also think about this in terms of electric potential energy. And if you go back and look in the notes or in the textbook, you'll see that's the negative of the dot product of those two vectors, the electric dipole moment and the electric field, and that is a scalar quantity that's equal to P times E times the cosine of the angle between those two vectors. That's the dot product between any two vectors. Now with this information, we should have enough to go to our evaluate step to think about what is the condition here for zero torque or zero potential energy. So we can see that the torque will be zero when we have this sine theta being equal to 0. And if you think about your sine function, that will be when theta either equals 0 degrees or 180 degrees, or we might also think about that as 0 or pi radians. Sometimes we like to think about these angles in measure of radians. And we can see that the potential energy, the electric potential energy of the system will be 0 when the cosine of theta will equal 0. And you can see that will be when theta is either plus or minus 90 degrees, if we think about that angle there, or of course that could be plus or minus pi over 2 radians. It's important to think about what these angles are telling us from our diagram there. So if again we have our electric field here, we can see that in terms of that dipole moment, having it either 0 or 180 degrees is saying that our dipole moment there is either aligned or like anti-parallel with our electric field, and that will be when the torque equals 0. And then this other case here is when we've got our dipole moment here either at right angles in one direction or at right angles in the other direction, and that will tell us when our potential energy of our system here is 0. So to answer our question, which we can do now, we can see that the answer here is no. We don't have the same conditions for 0 torque and 0 potential. We must have different conditions applying, different orientations of our dipole there to get those things to be 0. So different conditions for torque to be 0 and potential energy to be 0. And that answers our question, thinking about our relationships here that we know. It's important now to do an assess step, giving ourselves a bit more room here to put in an assess step. Thinking here again about our electric field, and we could say, well, trying to understand when the torque is going to be 0. Remember, that's when we said when the dipole moment was either parallel or anti-parallel to the electric field. What that's telling us, of course, is that our charges must be joined by a line that's parallel to the field. Now we know the forces on those charges. The force on a charge from an electric field is going to be in the direction of the field or in the opposite direction, depending on the positive or negative charge, but it's going to be along the line of the field. And you should be able to see from the diagram, those forces are clearly maybe going to try to stretch out or compress our dipole, but they're not going to be trying to rotate it. There is no torque that comes from those forces. So that really clearly explains why we expect our torque to be 0 for those conditions there. Now when it comes to thinking about the potential energy, it's a little more complicated. You've got to think a little bit about what that's telling us. Imagine we had our dipole just slightly off being aligned with our field lines here. We can see there will be a torque acting upon our dipole here. In fact, if we have this as our positive end and this is our negative end, we should be able to see the forces here are going to be one in that direction and one in that direction. And that is going to give rise to a torque. It's going to try to rotate our dipole around in that direction there. And in fact, as that dipole would be rotated in that direction, there'd be positive work being done by our electric force. But our change in potential energy, remember, is defined as the negative of the work. So in fact, our potential energy there will be getting lower and lower as our dipole rotates around. And the point of lowest potential energy would actually be when our dipole, rather than being sitting in that orientation, when our dipole is actually aligned with the electric field, that's our lowest possible potential energy. However, the convenient definition for us to make for our 0 point of potential energy is actually when the dipole moment is at right angles to the field. That's when we've defined the potential energy to be 0. You might recall that for potential energy, we do have some leeway as to where we define our 0. And the convention that we use here is the 0 potential energy for our dipole in an electric field is when the dipole is at right angles to those field lines. And that kind of explains why we do get this result here, that when our torque is 0, it's not when our potential energy is 0.